non-homogeneous linear differential equations. And I've got a little bit of a lead in for that. And the lead in starts with formatting. So we already talked about the format of our linear differential equations. And we said, hey, our format is all of our terms that have y's in them do not have the y's raised to any other power other than the first power, and that includes regular old dependent variable y and all of the visible derivatives. All of the coefficients on y, and I'm including these functions right here with a funky name for p. So the guys with the independent variable, totally fine to have independent variable, but you're not allowed to have any of the y's. You add up all the terms, and so all the terms with y are on one side, and all the terms without the y are on the other side. And a non-homogeneous differential equation means that this guy over here, the f of x, that guy can't be 0. Okay? Now that little comment's about to fly away just because of how these slides are put together. So we've already talked about homogeneous linear differential equations. Notice the only difference here is the difference between homogeneous saying that you have to have that 0. The non-homogeneous says, no, you're not allowed to have 0. You actually have something like a 2 or an x squared. It can't have any y's terms in it, but you're also not allowed to have no term. So it's legitimately a term that has only independent variables of some sort in it, or non-zero, linear, independent variables, excuse me. So here's the new terminology that we need. The first one is something called a particular solution. In terms of its symbol naming convention, it's denoted by a little teeny tiny p in the subscript. It stands for particular solution, and it's the particular solution of our non-homogeneous differential equation. So that guy up at the top that doesn't have an equal 0. Don't overthink this one. When somebody says a particular solution, you literally could guess and check this guy, and you just find some function that when you plug it into the differential equation, the equals is true. Now, that being said, guessing and checking for your particular solution is a dumb move to do. Why? Because it's normally too complicated to find just by normal random guessing and checking. Okay? So we're actually going to see a couple of different ways to find this particular solution. And the first one is the smart way to guess and check. And then after that, there's a way where we actually have a formula that you plug it in. And every semester that I teach this course, my husband and I get into an argument about which of those two methods is easier. I think the guess and check method is easier for a lot of things, and he, because he loves formulas, says I would much rather just have a formula and drop everything into it. So you may prefer one method or the other. We're actually going to go over both of them over the next few class times. In terms of terminology, we are going to need also something called the general solution of the homogeneous function or the associated homogeneous function, or as some people prefer to say, they'll just say the homogeneous solution. Oh no. That was terrible. We'll pretend that actually was not a scribble. Some people just call this the homogeneous solution. Notice here in terms of symbols, it's got that subscript of an H, and that's why last week I tried to, at least some of the time, say that our solution was really Y with a subscript H, because we were solving for the solution to the homogeneous differential equation. Now we'll need to look at our associated homogeneous differential equation, do the same thing we did last week, but now we have an extra component of dealing with our particular solution. Now, why do we need to deal with both of them? Because the actual general solution to your non-homogeneous differential equation, which I'm going to call Y, like your book does, although some books, I think this is what my textbook did when I was taking this course, it actually called it Y of G, G to indicate the general solution of the non-homogeneous differential equation. Doesn't matter to me which of those two symbols you use, but just note that both of those two guys are pretty common to refer specifically to your solution of the non-homogeneous differential equation. And here now is the format of that solution. So if you find the general solution of your, that was trying to be a G, if you find your general solution of the non-homogeneous differential equation, it is literally your homogeneous solution plus your particular solution. I'm going to attempt to make my handwriting less crazy here in just a second. Sorry about that. Huh. Now, one last comment before we get into our method of dealing with how we figure out what our particular solution is. And that comment is, we already know how to find our solution to the homogeneous differential equation, so the only new thing for the rest of Chapter 4 is just going to be finding that particular solution. Like I said, there's a couple of different ways to do it. We're only going to talk about a couple of them, and you can find in your book or in other textbooks, or probably if you Google it too, I'm sure, you'll find extra solution, extra methods. We're going to focus in on two main ones, which is the method of undetermined coefficients, which we'll start today, and the other one is called variation of parameters, which realistically will start next week at some point in time. The last method we'll talk about is dealing with solving differential equations using Laplace transforms, and that one is a little different because you don't find the particular solution, you actually find the particular solution and the homogeneous solution all at once. So a little different. But you don't have to remember that right now. All right, so that's the terminology that we need to remember. Let's look at an example. So suppose you're given the following example. Suppose you've got this second order differential equation, second derivative of y minus 4y equals 12x. And suppose you're told what a particular solution is, and after I already typed this up, and when it was too late to fix it before class, I realized there was a typo. That particular solution should actually be negative 3x. So here's what we want to do. We want to go and figure out what is the solution of the non-homogeneous guy. So here's the procedure. Step 1. So the first thing you want to do, and technically step 1 and step 2 could be interchanged, but I would recommend finding your solution to your homogeneous differential equation first. Now here's the fun part. You're not given a homogeneous differential equation. So if you look for a homogeneous differential equation, you are looking for the homogeneous differential equation that is associated to what you're currently given. Pretend we did ODE there. So the associated homogeneous differential equation is literally you write down exactly what you're given, except instead of writing the term that has no dependent variables in it, replace that term with a 0. Notice our differential equation looks almost identical to the one we were given, except now it's homogeneous. And at this point, we're going to solve this homogeneous differential equation the same way we would last time. So the first thing that we did last time is we grabbed our characteristic equation. And for our characteristic equation, we had to convert our dependent variables over to exponents. And we don't need all of these, but we've got a second derivative and we've got a regular y. Does anybody remember what the second derivative would convert into in terms of, your book uses r, so I'll put an r over there. Feel free to use the little chat. It is something that you're able to type in relatively easily. Excellent. At least 2 of you remembered. Yep. So second derivative turns into r2. Anybody get what first derivative turned into? So first derivative turns into regular old r, and if you were really pedantic, you go ahead and put a 1 there. It always surprises me how electronic things that you write turn into smears. And then the last one, which is your regular old dependent variable y. Anybody remember what that one turned into in terms of r? Ooh, I like. One of you gave me the full thing. So yep, this guy would turn into r to the 0, or exactly the same thing as just plain old 1. So when we rewrite this current homogeneous differential equation and grab its characteristic function, you just replace. So we'll get r squared minus 4 equals 0. And I on purpose picked something that we could easily factor. Anybody grab what the factors of this is? Factors are, excuse me. I'll do the easy part. There's r's inside the parentheses. Ooh, I got it. Yes. R plus 2, R minus 2, which means what are our two roots? Yep. Oh, you guys totally anticipated me in terms of asking that. Or I just didn't look up at the chat room quick enough and you'd already answered. Awesome, guys. So yeah, we'll get positive and -2 for our roots, which means in terms of our, oh, we accidentally did in terms of last time, the first two steps. So we are ready to go ahead and grab what our specific solutions are. So if we go ahead and grab one of the solutions, if that guy corresponds to, say, 2, what should I write down? It should be e raised to something. Anybody remember what the exponent would be? So you're going to, so we'll use the 2 and the -2. So y1, if it corresponds to root 2, we'll have a 2. And what's the independent variable currently in this differential equation? Anybody spot who the independent variable was? Because last week we got to choose, and we said it was standard to pick t's and x's. But with non-homogeneous guys, yes, it is actually normally given to you specifically right there in the non-homogeneous part, the part that's not equal 0. That tells you, that 12x there tells you that our independent variable has to be x. So here, there's no ambiguity. You know what it's going to be. And then if we grab our other root, the -2, we'll get e raised to the -2x, which means put it all together, and we'll have that our homogeneous solution is going to be c1 e to the 2x plus c2 e to the -2x. Everybody okay so far? Not seeing you guys is difficult, but at least some of you are typing. Awesome. Feel free to use the green check marks too, if that helps. So we've got the homogeneous solution right now, or the general solution of the homogeneous differential equation, or the associated homogeneous differential equation. So step 2 is going to be finding a particular solution. Now this is, for this example, already given. So this tells us, hey, bam, just copy down what was given in the actual question. Make sure you change the typo that unfortunately I found too close to when we actually started talking with each other today. Now, step 3, and this is the last step, is we want to find the general solution of our non-homogeneous differential equation. So this is where, don't overthink it, you're just going to add the answers from step 1 and step 2. That's it. Don't overthink it. This class, by far, you know, you've done these problems before, you can overthink things very easily. We're tedious, there's lots of steps, there's lots of details to remember, but that being said, don't overthink it. So in our case, our general format is we're going to have the homogeneous solution. So we'll have our c1 e to the 2x plus c2 e to the -2x, and then we will add our particular solution to that. In this case, that would be the -3x. And that right there is the procedure for pretty much any of these non-homogeneous differential equations. The only thing that makes these problems, well, take longer than the homogeneous solutions is you have the step 2 and step 3. Step 3 is nothing. Get step 1, step 2 together, get those two different answers and add them to get you your final answer. But the big thing that we're going to focus on for the rest of chapter 4 is the various ways that you can find your particular solution. So each of these two main methods that we're going to be using are all focused on step 2. It's just getting to the particular solution. So the rest of the examples that I have today, they're not going to really say much about the homogeneous solution. They're not going to say much about the general solution right over here either. We're just going to be focused on getting the answer to our particular solution. And then in the future, we'll go and put all of this together again. Questions before we move on to the actual method for how do you pick or how do you figure out your guess for your particular solution? In other words, a method for dealing with step 2. Any questions before we move on? All right, seeing none, I'm going to go ahead and move us to look at the actual solution. Okay. So this is called the method of undetermined coefficients. Normally I say, if you don't remember the name of this thing, no worries. But this time, because, and it's not going to be on test 2, it'll be on test 3 most likely, you'll have a question that says something like, hey, use the method of undetermined coefficients, and then another one that says, hey, use the method of fill in the blank for the next method. You'll want to at least remember it short term for a little bit. Okay. Now, nice thing about this method is that name, undetermined coefficients, is 100% a description. Nothing more than that. So here's what you need. First thing you need is we are assuming that we have some differential equation. We are assuming that it is a non-homogeneous differential equation. So that term over there with no y's has to not be 0. Why? Because if it is 0, we really have a homogeneous equation, and we just use the characteristic equation like what we did last week. Okay? The other thing we're assuming here is we are assuming that we have constant coefficients. What that means is in front of all of those y terms, whether it's regular old y or any of the derivatives of your dependent variable, your only constants and constants as really just a real number. No independent variables allowed. No x is allowed whatsoever. Okay? It turns out if you do have any independent variables right here in your coefficients, method of undetermined coefficients doesn't work and you've got to use a different method. Okay? So, to remind ourselves, the solution that eventually we're going to try to get to for a non-homogeneous differential equation is the sum of the homogeneous solution and the particular solution. And our method of undetermined coefficients is going to find specifically that particular solution. Now, what the method of undetermined coefficients does is it provides a guess for you for that particular solution. And what you look at is you look at the non-homogeneous part of your differential equations. And what you do is you just set your guess to that function, lie. You set it to the same format of that function. And we'll have some examples in just a second for what I mean of format. So once you have your guess for your particular solution, we're going to plug that guess into our differential equation. So you have to compute all the derivatives of whatever you think the particular solution should look like. You plug it into your differential equation, you make the equals stay equals, and you'll solve for anything that you don't have. Hint, as soon as we get this general form of our guess, you'll see what I mean by solve. Specifically, you'll have arbitrary coefficients involved, and you have to solve for them. So this name of undetermined coefficients means we don't know what the coefficients are. We made a guess on format, then we solve for the coefficients. So I guess what you could really say is this is a method where you determine what those coefficients are. But that was just a mouthful, so we don't call it that. And then that last thing is the solve for your unknown coefficients that you get in your particular solution. And here's the warning at the end. Don't forget this method is only going to give you your particular solution. You still have to go ahead and grab your homogeneous solution from using your characteristic equation, and then you grab the particular solution from method of undetermined coefficients, add them together, and that's your final answer. So when you're working these problems all together, where you have all three of those parts, find your homogeneous solution, find your particular solution, add them together, it really feels like two complete problems that are put together. Step 1, homogeneous solution. Step 2, particular solution. I mentioned that several times because it's really easy to just go in and find the particular solution and completely forget about the homogeneous part. So this is going to talk about the format and how to get your guess for the particular solution. The first part is stuff we already talked about. You got some differential equation. It's non-homogeneous, so you've got a non-zero part right over there. And we've got all of these constant coefficients in front of all the terms with y. So here's your formatting. There's three main types of functions, and when I say functions, I am talking about that non-homogeneous part of the differential equation. The first one is it looks like a polynomial. The second one is it looks like an e raised to some power. And the third one is it looks like a sine or a cosine. Okay? If you don't have those three types, for your non-homogeneous part of your differential equation, method of undetermined coefficients isn't going to work for you. Polynomial is self-explanatory, but for your exponential guy, it's got to be e raised to some constant like a c times x. And for the sine or the cosine, it's got to be sine with some constant like a c times x, or cosine, some constant times your x, or whatever independent variable you actually have. Now, one of the things we're not going to see today, but we will see in the future, is you can actually have a non-homogeneous differential equation where you've got this non-homogeneous part right here, and maybe it's part polynomial, part exponential. You can adjust the method of undetermined coefficients to deal with that just fine, and we'll see how to do that in the future. So key things to remember, you got to have your constant coefficients, and your non-homogeneous part of the differential equation has to match those three, one of those three formats: polynomial, exponential, or some sort of trig. And please note, this trig is either sine or cosine. It does not include the other trig functions like tangent, like secant, cosecant, cotangent, arctangent. Those guys are no-go. It's just sine or cosine. All right, so this tells you types of functions. Still hasn't gotten us to the nitty-gritty details, so here's the actual details. Oh, we can move to the next thing. Just a second, my screen froze. All right, so that should still work on your guys' end. You guys still seeing the same thing? I made it a little different on my end, but since I'm only sharing the PDF viewer, it should still look the same on your end. If you guys see something weird, let me know. All right, so let us move to where we were at. All right, so this is the next guy. So breaking down those three main types of functions. Suppose you have a just a second. Again, that should not be affecting what you guys see, hopefully, but it definitely just affected what I saw. I pushed the wrong thing. All right, so if you are looking at a polynomial, suppose your non-homogeneous part look like that polynomial. X to the fourth plus 3x squared minus 1 is an arbitrarily picked polynomial. The only thing about this that I picked was that it wasn't a super simple polynomial, and I on purpose chose to have a couple of the terms below x to the fourth missing. Now, if you wanted to get your guess, here's the thing. Your guess for your particular solution needs to match that same format. So what's the key thing in the format here? Your key thing in your format is the fact that this is a fourth degree polynomial. So fourth, there's an R, degree polynomial. Now, there's no guarantee that your guess for your particular solution is going to have the exact same coefficients of the fourth degree polynomial for your non-homogeneous part, the f function right here. But it won't be any polynomial that has a term bigger than degree 4. Maybe your coefficient a right here is 0, unlikely, but maybe. Maybe some of these middle guys over here are also 0, but they're probably not going to be the same coefficients that you had in the exact given non-homogeneous part of your differential equation. So when we talk about the undetermined coefficients, right now the coefficient A, B, C, D, and E, they are undetermined, meaning we don't know what they are. And what will happen is we would plug this expression into whatever differential equation our non-homogeneous part came from, and then we would solve for A, B, C, D, and E. No, we're not going to do one like that today. I've got a polynomial example prepped up for us, but it's way smaller, so there's not so many unknowns. And that's it for polynomials. Polynomials are relatively straightforward when it comes down to your guess, probably the easiest among, I shouldn't say easiest, but the same as exponential. So that's it in terms of polynomials. Now, in terms of exponentials, the key thing to watch out for exponentials is if your non-homogeneous part, your f of x here, is e raised to something like x squared, we can't really handle it. But if it's e raised to a constant times x, like this 4x, that is something we can handle. So what's the general form of this guy? Well, it's somebody that looks just like him, except maybe there is some coefficient out front. Not going to lie, this one here is probably my favorite one to get, just because we literally have one unknown to solve for. Now, there is something that can happen, and this can happen. You see it most often with exponential, but it can also happen with both polynomial and the trig form of the non-homogeneous parts. When you make your guess for your particular solution, it is possible that when you plug this guess into your differential equation, it doesn't work. And we'll see an example of that either at the very end of today, but more likely next time. If it doesn't work, what will happen is instead of in your differential equation, you get whatever the non-homogeneous part is, you would get an equal 0. Well, what's the fix? It turns out the fix is put an extra factor of your independent variable out front. If you get the equal 0, it means this guy really was one of your solutions from your homogeneous guy, and we need somebody who's fundamentally different. So that same trick with the double roots that we had last week is you throw on an extra factor of your independent variable. But we're not going to focus on the stuff inside the parentheses today. We'll talk more about that in the future. And then the last type of function that we would see for our non-homogeneous part of the differential equation, this f part, would be what happens if you got a sine or a cosine. Now, again, key, you do have to have a constant times your independent variable. So if you had something like sine of x squared, this method wouldn't work. But if you have sine of, say, 3x, that would work just fine. Or cosine of 3x, or it actually works if you add them or subtract them together too. In this case, this is the one that looks the most different of all three of the cases. The guess here, and it doesn't matter if you originally had your f function as either the sine or the cosine, the guess is exactly the same. And that guess is some unknown coefficient times the sine plus some unknown coefficient times the cosine. Now, here's the reason why these guesses are what they are. Specifically filling in all of the missing potential derivatives. Because remember what happens with your guess. You're supposed to plug it into your differential equation. The various terms of your differential equation deals with derivatives. So you have to make sure when you plug everything in, you're covering all of the derivatives that could possibly come up. Derivatives in terms of polynomials are what? They just drop an exponent. So that's why we needed to make sure we covered those two terms of the x cubed and the x to the first power. In terms of e to the x, or e to the 4x in this case, or e to any constant times x, the derivative is the same thing, but maybe some constant out front. In terms of sine or cosine, the first derivative of each is the opposite, which is why you want to include both the sine and the cosine, because that makes sure that you're picking up any derivatives you might have in your differential equation. Okay, so that's the theory behind what we've got. Everything else that I've got prepped up for this section is just a bunch of different examples. We'll probably get through, I don't know, with the time left, depending on the questions that you guys ask, if any, we'll probably be able to get through somewhere between 2 or 3 examples. And then anything that we don't get to today, we'll talk more about next time. So the first example I've got for us goes as follows. It is only asking us to find our particular solution. Notice here, it is not asking us to figure out what the general solution is for this differential equation. So this would be where previously to the work we're about to do, you'd already have a step 1. So let me signpost that, but not actually do the work. So here, step 1, find your homogeneous solution. We're going to skip that for today. Step 2, we're going to go ahead and find our particular solution, specifically using our method of undetermined coefficients. Let's pretend that horrible scribble is a P. Actually, I think I can get rid of it. There. So in my other class today, we were in PowerPoint. You can't undo marks in PowerPoint, but this one we can. Awesome. All right, so in order to find our particular solution, the first thing that we want to do is we want to make a guess. That was trying to be an A, so we are going to guess YP. Now, based on what we just talked about of the three formats of our types of non-homogeneous parts of our differential equation, anybody have a guess on what format the particular solution should look like? Don't overthink this. Oh, I like how you wrote that. Can I be super lazy and not use the E? So I'm going to go ahead and guess here. Yes, A times the highest power of X, which is just the first power. You don't need to write the 1. I'm now regretting it, so let me get rid of it. Plus now the constant term. And if you pull exactly what we did on the previous page, we called our constant term E. I'm going to be super, super lazy and just call B, mainly because I can write it quicker and with more accuracy than an E. Okay. Now, what do you do once you make your guess? The next thing we're going to do is we're going to plug this guess into our differential equation. Okay? Make sure you plug this into the non-homogeneous differential equation. So a little bit of background is every time we check solutions, remember, the particular solution is still supposed to be a solution of this differential equation. We had to make sure we had all versions of y. So original dependent variable, first derivative, second derivative, third derivative, whatever derivative you actually have. So in our case, our highest derivative is what? I'm going to leave that up to you guys to tell me. What's our highest derivative? So if we look at our second derivative, and I'm going to go ahead and put the subscript of p on this guy, just so we remember what we're doing. We're going to need to find that second derivative. We're also going to need to go ahead and find our first derivative, because we can't get the second derivative unless we have the first derivative. And we already have the original guy, so let me go ahead and put the original one right down here at the bottom. So I'm going to work my way bottom to top, just because that's typically how derivatives go. Yes to all of you. So first one is just copy what you guys said before, which is ax plus b. Pretend that a doesn't look like a triangle, so let's fix it up. That didn't look much better. Pretend that's an a down there. So first derivative is going to be what? I'm going to throw that out to you guys. The first derivative is going to be an a, and there's a reason I picked this example, because it's awesome. Anybody got what the second derivative is? Yep. The second derivative here is totally going to be 0, which means when we start plugging this in, so I'm looking right up here at our derivative. That's not a derivative. At our differential equation. So if we plug in second derivative, I'm going to go ahead and signpost what we're doing here, plus 3 times the first derivative. And notice here, just to tell future self or any readers such as yourselves what I'm doing, I'm going ahead and putting those subscripts of p still on here. I'm going to go ahead and actually write the far side of the equation as well, because we're going to drop in and then solve. Our second derivative was 0. Our first derivative was a, so that's 3a. And the only thing that even has a little bit of work on it is the regular old function, which was the 4 times, well, 4 is in the coefficient, but the original function was ax plus b. And then we've got the 3x plus 2 on the far side. All right. Any guesses what we're going to do next? Hint, it's totally just going to be algebra. Our goal here is to solve for a and b. Any guesses how we would solve for a and b? It's a strategy, and the first step of the strategy would be to do what? Any guesses? And then there's utter silence. Ooh, yes, there are good guesses. So it depends on what you want to do. Yes, distributing that a to the a, that 4 to the ax plus b, definitely a good thing to do. Also, we definitely want to, it would be a good idea to isolate your a and your b. It would also be standard in this situation is to group like terms by the x's. So if we go ahead and group like terms, if we distribute this 4 there and there, we're going to get 4a times x plus, and then we get 4b And I'm on purpose putting parentheses there because what can be added to the 4b? Anybody pick up what can be added to the 4b? Yep, that's 3a. So here's what's up with polynomial equations. You can always combine your like terms, which means your terms with x on one side are supposed to be equal to each other. So this gives you a system of linear equations. This tells you that 4a is supposed to be 3. Well, if 4a has to be 3 from the x terms, that tells you that a has to be what? Divide by 4, so you get that 3/4. And second part is the constant terms on both sides of the equation, I'll underline them with a squiggle, are supposed to be equal. So this would be 4b plus 3a is supposed to be equal to 2. Wow, that was really sloppy. I'm sorry about that. Let me read it out. So 4b plus 3a is supposed to be 2. What would you do next? You'd plug in a equals 3/4. You'd solve for b. And are you guys okay if I just go ahead and tell you what that fraction would be? Feel free to vote with check marks. All right, it looks like the majority of you are saying, yes, you're totally cool with that part. So if we go ahead and solve for b, b should equal -1/16. So notice, all of the work with this particular method is where you figure out your guess, which is relatively minor. You then figure out your derivatives, normally relatively minor except for a few special cases where you have a crazy looking guess for your particular solution. But all of the work really is you plug in that guess and then you're solving for those unknown coefficients, A, B, whatever you call them. Standards are to use capital letters, just like when we were back in partial fractions. Then we're ready to go ahead and grab our last step. Our last step is to say, hey, I grabbed my guess from previously, that ax plus b, and I'm now going to plug in the a and the b. So this tells us that our particular solution of this differential equation is 3/4 x minus 1/16. And if you were trying to solve this general solution, the actual solve for the differential equation all the way through, you would have a last step, which we are going to skip today, which is find the actual solution, which is simply the sum of the homogeneous solution and that particular solution we just found. That right there is all the method of undetermined coefficients is. Got 3 parts. The actual method of undetermined coefficients is really only that second part. But in terms of how you use it, it'd be in conjunction with all 3 of those parts. First part with homogeneous solution. So right up here in step 1, this is where you'd use your characteristic equation. Step 2, we applied method of undetermined coefficients. Step 3, add the 2 answers together. And that is literally it. That can work any time method of undetermined coefficient works. Questions? Make sense? Feeling okay-ish so far? See a couple of you voting with green check marks. Those things are awesome. All right. Well, let's end there for today, because the next example deals with trig functions, and trig functions take a little bit more time just because your guess has to deal with both sine and cosine, and then you have to take all the derivatives. So next time what we'll do is we'll come back and we'll look at examples of trig functions and exponential functions and how they work. Exponential functions work exactly the same as this. No big deal. Trig functions have a tendency to be a little bit long when you start going in and doing the algebra part here at the side, but still the exact same